Welcome everyone. We are team TriForce Analytica. We are Elijah, Henley, and Magnus, students in Master Degree in Data Science program. Our project title is Leveraging Machine Learning for Advanced Crime Prediction in Los Angeles. Today we are presenting Chapter 4, the result. Our journey reached to the Chapter 4, the result, an exciting part of our study. In this slide, we are going to present our 3 hypothesis questions with respond and get answer around those questions. And what we are going to use the algorithm to get our answer. The evaluation metric that we use to evaluate the models that build. The detail of our prediction analysis for crime classification and crime occurrences hotspot. Last but not least, our preliminary result of what we found in 34 models that we built. The text of Hypothesis 1 through Hypothesis 3 are actual questions in our paper from Chapter 1 and Chapter 2. To answer Hypothesis 1, the spatial temporal crime hotspot within the district, we are using 2 algorithms of time series, the ARIMA and LSTM, with 5 models as listed in the slide. Therefore, in total, there are 10 models of time series analysis we're going to share. Regarding with the hypothesis 2, with the weather condition correlate with the crime in accident and hypothology, and hypothesis 3 regarding with the significance of victim demographic in patterning crime. For these 2 hypotheses, we are using crime type as the category classification with 6 algorithms, multiplied by 4 models. Example, all relevant predictors, or relevant predictor without weather, or relevant predictor without victim demographic, and all relevant predictor without weather and victim demographic. So for the categorical classification model, we got 24 as the result. Following the previous slide, we are using the time series to predict hotspot of crime by using ARIMA and LSTM. The 5 bureaus are originated separated by LAPD. Example, the South Bureau, West Bureau, Central Bureau, Valley Bureau, and the whole LA. The model will be evaluated by root mean square error. For second category of our prediction, the crime classification category, there are 4 basis models and applying 6 algorithms. Therefore, we got 24 models. Each model will be evaluated by accuracy, precision, recall, F1 score, mature correction coefficient, Cohen kappa, and log loss. Next, I will pass to Magnus to continue for detail.
Hello everyone, and thank you, Hengley. To predict the crime occurrence or crime rate in LA based on hotspots in areas, we shall group the 21 geographical areas into their bureaus as categorized by the LAPD. These 4 bureaus, namely Valley, which has 7 areas, Central with 5, South with 4 areas, and West with 5 areas, would then be the basis for predicting crime rates based on the daily number of crime incidences that occurred in the region. Now, crime occurrences in LA as a city will encompass all the 21 areas. 2 time series algorithms, namely ARIMA and LSTM, will be used to predict the amount of crime occurrence. Now, upon running a total of 10 models, 1 each for ARIMA and LSTM across all the 5 bureaus, we see that LSTM is the better model as it has less root mean squared error across each category. For the whole of LA, LSTM had an RMSE of 16.60 compared to ARIMA's 31.26. Amongst the bureaus now, Central had the best ARIMA model with an RMSE of 27.44, while for the LSTM, we have the best RMSE of 11.43 with Value Bureau. In order to classify the crime category across the four models, we reduced the initial 144 categories to 8 categories. Hence, we have 8 classes. Theft and burglary is the most dominant class. And to test for the effect of victim demographics and weather in predicting crime types or categories, we shall use 6 algorithms, each for the 4 models with varying predictive features. As you can see on the screen, Model 1 includes all the relevant predictors, while for Model 2, it includes every feature except the weather features. For Model 3, we exclude the victim demographics only and have all the other relevant features, while for Model 4, we exclude both the weather and the victim demographic features. Now over to Elijah on the results of our 24 models.
Most models performed with comparative accuracy ranging in the full range of the 70th percentile of accuracy. Other metrics such as precision, recall, and F1 score varied a bit more with respect to each model's strengths and weaknesses. Random forest showed the greatest classification power in almost every metric at nearly 80%. And a common trend shown within the varied data sets is that the predictive accuracy decreases very little to none at all if weather data is present or removed, while excluding victim demographic information decreases the model performance by as much as 10% in some models. Support vector classifiers and decision trees were generally the lowest performing, especially when the hypothesis variables were removed. We specifically use weighted metrics to help address the class imbalances when predicting the different crime categories. Additionally, we created a downsample version of the data set where each crime category contained about 57,000 observations to further address the large imbalance in the target variable. All downsampled models performed significantly worse by about 10 to 15% in each category, but the investigation point helped understand the impact of class imbalance on the data set. It appears that having more data and using weighted metrics is a better way to address class imbalance than downsampling for our data set. We wanted to ensure we analyze as many metrics as possible when measuring the effectiveness of each algorithm, so we included Cohen's kappa, Matthews correction coefficient, and log loss to better understand each model. We purposely omitted receiver operating curves and AUC as they are more suited to binary classification problems, and we didn't want to use one-to-one versus one versus all metrics when assessing crime classes. So Cohen's kappa helps us assess and adjust for chance agreement to help measure model performance in an imbalanced data set, with a value of 1 being perfect predictions. Matthews correction coefficient shows a similar performance metric by assessing the calculations of true and false positives and negatives to help assess the model's performance across categories, also with a value of 1 being perfect. We also use log loss as an assessment metric to assess model performance with penalized incorrect classifications and assessing the confidence of predictions with a value of 0 being ideal. In nearly every situation, random forest showed the highest Cohen's kappa and Matthews coefficient, as well as close to the lowest log loss, and again, outperformed many other models. It overall appears to have the most consistent ability to analyze this data set and discern between crime categories with or without victim and weather data. So to better help visualize the last 2 slides, the initial finding of the results of victim and weather demographics impact on crime, this line chart shows a comparative analysis on how each model's accuracy changes as the predictive variables are adjusted. K nearest neighbors is a performance anomaly, as it's still in the process of having the amount of neighbors adjusted to optimize its performance. As you can see how it trends upward as we remove variables. With this visualization, we can clearly see that victim demographics causes a large impact on the predictive accuracy of our models when determining crime categories. We arrange this line graph to see the large jumps when including or removing victim information, and the minimal jumps in accuracy when removing or including weather information. There's minimal impact when weather is removed. So far, our initial findings in respect to our research hypothesis is that victim demographics do play a large role in types of crime, but weather appears to not have much of an impact on types of predicted crime. So to summarize week 1 of us working on our Chapter 4, the results section of our capstone, we've started building, tuning, and assessing model performance to answer all research hypothesis questions. So far, our initial findings are suggesting that one research hypothesis weather information's impact on crime prediction may be disproven, while the others are still showing favorable results. We were able to develop successful models for spatiotemporal analysis to predict crime types by location, and we're seeing a measurable change in performance in all machine learning models depending on the presence of victim information in the data set. Thank you so much.